Welcome back. And now the second part of technical shortcomings in machine learning. Here are some of the related objectives to this lecture. And again, just as with part one of this lecture, this is based on a paper called Deep Learning: A Critical Appraisal by Gary Marcus. We're not covering everything in the paper, but we're covering the things that are relevant to our course objectives. And also, just like I said in the last one, many of the things that Marcus brings up are relevant to much more than deep learning. Many of the other methodologies in machine learning, these are appropriate critiques as well. So here's a list of some of the challenges, and this is what we'll cover in today's lecture. All right, so the first one is that deep learning is not integrated with prior knowledge. And what does this mean? Well, he gives some examples, and these are things that we can answer these questions without any kind of training data. So you could ask the question, who is taller, Prince William or his baby son, Prince George? Now, you could have no idea who either of these people are, but right away by reading the sentence, we know that, well, if it's his baby son, he's going to be likely smaller. So that's how we would answer that question. Can you make a salad out of a polyester shirt? You're going to answer no, because you know polyester shirt is not a food, not something you could make a salad. You know that a salad is something you could eat. But again, you can do that in your head. No one ever had to tell you before you saw this slide, give you a pile of data about things you can and cannot make salads out of. If you stick a pin into a carrot, does it make a hole in the carrot or in the pin? And so, think of this is a lot to do with the context of the sentence, but we all know that, a pin is much smaller, it's much pointier, it's sharper. And so if we stick the pin in the carrot, and we know that carrots are really easy to cut and slice and make holes in, we know it's going to make a hole in the carrot. Again, we all know the answer to this question because we're familiar with pins and carrots. This is an example. The prior knowledge you use to answer all these questions, as I walk through those, is what are called common sense knowledge. And in most of deep learning today, there's no really good way to integrate that in. Well, there's a couple who are doing some initial work on it, but there's no commonly used way to integrate this in that gives really good results. So, and again, for these questions above, training on historical data, it just doesn't make sense. Why would you want to train on data about, everything that could be, ingredients in a salad? You shouldn't have to do that. You shouldn't have to do that for every, kind of question that you could potentially ask. You should instead be able to reason about the question. So why does deep learning fail with this? Well, it's designed from the ground up to learn from data and not pre-specified models. So it's even difficult to get that knowledge into a deep learning model to then reason about. So in addition to common sense knowledge, also physical laws like things Newtonian physics, aerodynamics, stuff like that can't really be embedded into a deep learning model. Now, there are some attempts, and I know some colleagues that are trying to integrate common sense knowledge into deep models, but that's still in its early phases. And part of the problem with doing so, though, is by taking common sense knowledge normally represented as something like a knowledge graph and embedding it into a deep learning model just the way we embedded text into deep learning frameworks we talked about earlier. Doing so, you're now sacrificing explainability. And so you could still have reasoning about something, but you have no idea why the system came up with the answer it did. So then the next point he brings up is correlation versus causation. And we'll start with a simple example outside of deep learning or anything like this. We have 2 time series data of things that happened over time and an annual basis. And you look at the black and the red line, and they look like they correlate pretty well. So what are these things? Well, this is a correlation between drowning deaths and films with Nicolas Cage appearing in it. And so clearly these have, 2 things have 0 to do with each other. You could say maybe if there was a time lag, maybe there might be, or some joke like that. But all that aside, this is clearly spurious. This is garbage. But, a machine learning model, and not even just a deep learning model, could easily learn this. In fact, here we only have 2 variables we're associating with each other. So you can come up with this correlation, with a simple regression model, not to mention a deep model, and it'll still say, still be predicting drowning deaths based on Nicolas Cage movies. Now, the correlation versus causation, this is a problem across very many machine learning models. And it all has to do with, you have this historical data. Is even anything in the historical data causally related to your target value or class label? Now, deep learning adds on to this existing problem due to the overparameterization, because the model is so big and is trying to fit as much data as it can. If you have data that is not related to the target thrown in there, deep learning model is going to do everything it can to make that data fit. The other thing to note is regularization. It does not address causality. I've gotten this question before. And so, you can even go back to our example of the drowning deaths in Nicolas Cage movies. Adding regularization, in that example would not have erased this correlation that would have been held up as being accurate. But again, this is the problem dealing with a lot of different approaches, not just deep learning. One of the many things that you can do to kind of examine this, in addition to running really good validation processes that, especially in certain domains involving real subject matter experts looking at your result, another thing to do is consider the data. Consider is the data I'm ingesting truly related to the target? So next we have assumption of a stable world. And so this is an interesting one. So let's say that I have some machine learning model. It's operationally producing for predictions for a long period of time, and for some given level of precision, it's producing a recall of 0.9. And all of a sudden, as shown in the picture, there's a big drop, and it goes all the way down to a recall of 0.4. It misses 3 of 5 predictions. Now, I tell this story because I've had this kind of thing happen to me in actually running a company with machine learning software. And it's honestly a bit scary because you don't know why that occurs. And it gets worse because what do you do about it? Because do you retrain the model? Well, if you do, then if you retrain the model and what happened in the past week was just a blip, was just an outlier, now you're retraining to account for an outlier and you're going to harm your model. So if you don't retrain the model and it happens that this was a move to a new distribution of data, then your model's not accounting for this change in the distribution of data. And so this is a very difficult situation to deal with. What decision do you make? And of course, if your model is not explainable, if it has, you can't be assured of the data distribution not being stable, you're going to have these issues. But like many supervised approaches, deep learning, of course, is tied to the training data. And, a change like what we saw, if it's because of a change in data distribution, you could be in a lot of trouble in a real-world deployment. But again, this is issues with many machine learning models. The times when I encountered this, we're actually using random forest models for that particular application. And so, other approaches are not immune to this, but it still is a major assumption that's taken and should be considered. So finally, we get to engineering difficulties. And deep learning models are really easy to build. So, if you've used things like TensorFlow or PyTorch, you found that really quickly. You can come up with a neural network in just a couple lines of code. But how do you maintain it over time? How do you debug and understand that, hey, maybe that layer I added in the last training session, maybe that's what's causing my poor performance today. Or maybe I should switch activation functions. How you debug that is very difficult to tell. And this also goes back to not having any explanation. Deep learning, while these type of engineering difficulties exist in a wide variety of machine learning models, deep learning, it becomes more difficult because the models end up being so big and complex. And so, if there was, some kind of decision made that turned out to be poor in that model, it's very difficult to pick out a piece of it. The other issue is that deep learning systems, even though they could be very big, they're not modular. So I'll give you an example. If you're thinking that if an airplane is being built, the way airplanes are built is the subcomponents are all guaranteed to have meet certain safety and quality standards. And by each subcomponent meeting those smaller standards, you know that the whole thing, you can be assured, meets some overall standard. There's no such thing in deep learning. It's kind of an all or nothing thing. Once the model's together, the components don't make any difference. It only matters what the whole entire thing does end to end. And this makes things difficult because those models are very tough to train. They use a lot of power and computation to do that training, and so it's very tough to deal with when you don't have modularity. So anyway, this concludes the second of our two-part lecture on shortcomings in machine learning. Stay tuned for more content.